I'm Antonio Iverdi, and today we're going to talk about Lab 4, which deals with the macroscopic view of DC and RC circuits. The purpose of this lab is to predict the behavior of circuits in both series and in parallel. We're going to measure the values for conventional currents and potential difference, and examine the behavior of ohmic and non-ohmic resistors and capacitors. The method being used here is using a Java circuit construction kit to simulate these real circuits. The results of this lab was the use of the CCK to record time and voltage values across a discharging capacitor to create a graphical model to calculate the RC, or in other words, the time constant of the circuit, using the slope of this graph. The experimental value was 5.995 seconds versus the theoretical value of 6 seconds. Some fundamental physics principles being used here are the conservation of charge. Current in is equal to current out. In the steady state, the conventional current is constant. We will also use the loop rule, which is that the sum of voltage difference across circuit elements must be zero. We're going to also be using the node rule, which says that the sum of the current into a node will equal the sum of the currents coming out of a node. And lastly, we'll be utilizing Ohm's law. For our initial calculations, the steady state, we said that the current at 1 will be equal to the current of 2. Using Ohm's law, we found the R for the series to be 147 ohms. The voltage of the battery was 3 volts, and then from there we can figure out the current by taking the voltage of the battery dividing by the total resistance of the series, and our current was found to be 0.0204 amps. Comparing this with our CCK result, the values are pretty close at 0.02 apiece. We also used the two 1.5 batteries as shown on the left, and one 47 and one 100 ohm resistor. The results are still the same when using a backwards ammeter. It still shows the same result of 0.02. When inserting a voltmeter, the ammeter is going to read 0.00 amps because the circuit is now open or broken, and the voltmeter is going to read 3 volts because the circuit is now open and broken once again, and this is going to measure the potential difference between point A, the red node, and point B at the black node. Now here we measure the potential difference between various spots as shown in the top right corner, and theoretically, due to the loop rule, the sum of the voltage differences across the circuit elements must be 0. This holds true experimentally as well. When taking different measurements between potential difference points, we find at point A, B, C, D, and E, F, we have values that are non-zero. When you add them all together and find the voltage round trip, you find the voltage to be 0, holding true with loop rule. And once again, the current is still 0.02 amps because the current is going to remain the same due to the conservation of charge. Shown here is the potential difference graph, as you can see in the points highlighted in orange. These are points where the voltage difference is negative, and as you can see, it kind of drops down both between CD and EF. Now we look at an ammeter with a 100 ohm resistor in parallel. In parallel, the ammeter has less resistance than the 100 ohm resistor. This ammeter is going to act as an ideal wire, and will have a path of lesser resistance. For this reason, the ammeters now read 0.06 amps instead of 0.02 amps. Shown here are the resistance calculations. On the left side we have the readings from the previous time, and by calculating the ohm of each resistor, we can find that the values are still pretty close. You take 0.96 volts divided by 0.02 amps and find that it's 48 ohms. Likewise, you do 2.04 volts divided by 0.02 amps and get 102 ohms. Now, listed here in my summary of the RC circuits. The left two photos, you'll see that when the 10 ohm light bulb, 200 mF capacitor, and 9 volt battery are connected in series, the battery lights up the bulb and charges the capacitor, as seen in the left two photos. And then in the right two photos, when the 10 ohm light bulb is directly connected to the charged 200 mF capacitor, the bulb starts out bright and then continues to dim as the capacitor discharges, bringing the current of the circuit down to 0, as seen in the right two photos on the bottom. As you can see here, we now timed how much time it took for both the 10 ohm light bulb and the 20 ohm light bulb, how much it took for the capacitor to charge and discharge. And the times, if they're not so clear in the pictures, are listed in the middle as well. Finally, we're going to look at a time-dependent voltage across a discharging capacitor. The circuit contained a 9 volt battery, a 200 mF capacitor, and a 30 ohm light bulb circuit. The voltmeter measured voltage across the capacitor spanning 20 seconds. Voltage and time values were used in this equation, Ln of delta V over delta V initial equals negative T over RC. We then had a plot of Ln of delta V over delta V initial versus the time yields versus time. It's going to yield a straight line with a slope of negative 1 over RC. RC is also known as the time constant of the circuit, i.e. when the voltage difference drops to 1 over E of its original value. As you can see here, we have our time and ln of delta V over delta V initial plotted in the graph, And as we described earlier, it has a straight line with a negative slope. And if you look at the slope constant of negative 0.1668, that will be used in our results to finally find our calculation experimentally for the RC. And we found that to be 5.995 seconds. Theoretically, RC would just simply be equal to resistance times the capacitor. So we have 30 ohms times 0.2 F, and that gives us 6 seconds. So very close. In conclusion, if an actual ammeter was used instead of an ideal simulated one, the measured current reading would be lower because a real ammeter would exhibit some resistance. Increasing resistance decreases the current, as according to Ohm's law. If a battery was used in real life without a resistor in the circuit, the ideal model used here, or the CCK, would predict that the capacitor would reach full charge nearly instantly. But in real life, batteries exhibit some form of resistance, which would slow down the process of charging the capacitor.